In this video, we're going to look at differentiating the inverse hyperbolic functions. We're going to do this in basically the same way that we would derive the derivatives of the inverse trig functions, and that's to first rearrange this so that it says sin y equals x, and then use implicit. So I need to be differentiating sin y with respect to x, and that gives me cos y dy by dx. And 1 over here. So dy by dx is 1 over cos y. So the question is, what is cos y in terms of sin y? Because then we can convert back to x. So we know that cos squared y minus sin squared y is 1. And that means that cos squared y is 1 plus sin squared y, which means that cos is the square root of 1 plus sin squared y, and sin y is x, and so this is 1 over the square root of 1 plus x squared. And as you'll see, the more we do this, the more you'll see the similarities between the hyperbolic ones and the trig ones. And the derivative of arc sine x from trig is 1 over root 1 minus x squared. Now it's just 1 over root 1 plus x squared. Now I just glossed over the fact that I didn't consider the positive and negative when I square rooted. Why am I just interested in the positive? Well, what does r shine look like? R shine looks like this. Like that. So its gradient is always positive, and therefore we do want 1 over the positive root of 1 plus x squared. Okay, let's have a go with our cos. Same thing, so pause the video and try this one for yourself. So we'll take cos of both sides. Cos y equals x, and the derivative with respect to x is sin y dy by dx, and that's equal to 1. So dy by dx is 1 over sin y. So once again, we're thinking, how do I rearrange this to get sin in terms of cos? And you'll see that if we subtract 1 from both sides here, we get sin squared y is cos squared y minus 1. So sin squared y is cos squared y minus 1, which means we have 1 over the square root of cos squared y minus 1, which is 1 over the square root of x squared minus 1. Again, big similarity with the derivative of arc cos there. Again, I just took the positive one. Why is that? Well, it's because our cos looks like this. So it's always got a positive gradient. It's also worth noticing that the r cos function is only defined for x values greater than 1. And you see that here, x, as long as x is greater than 1, we don't get a divide by 0. We do, by the way, have a little undefined moment just when x is 1. X actually can be 1 on the r cos function. It just has coordinates 1, 0, but its derivative just at that point is infinitely high. Right, let's try our tanh. It's going to be very much the same thing. Tanh y is x. When I differentiate tanh, we've seen that we get sech squared y, and then it's dy by dx equals 1. So the trick here is to notice that we've got a nice way of converting sech squared into tanh. So rather than having dy by dx as cos squared y, which is correct but less useful, we're going to write 1 over sech squared y. So what's the relationship here? Well, cos squared y minus sin squared y is 1. Always come back to that one. Dividing through by cos y gets me 1 minus tanh squared y equals sech squared y. So sec squared y is 1 minus 1 minus tanh squared y, which is 1 over 1 minus x squared. So my derivative of r tanh is 1 over 1 minus x squared. Again, nice little connection with trig, where the derivative of arctan is 1 over 1 plus x squared. There's no positive or negative consider here, but it is worth thinking, well, hold on a second, what happens when x is 1 or minus 1 or something like that? It's not an issue because r tanh looks like this. It's got vertical asymptotes at 1 and minus 1, so it only exists between minus 1 and 1, and always has a positive gradient, and that's what we find. As long as x is between minus 1 and 1, I always get just a positive number here, which matches the positive gradient of this curve. Okay, if it feels like there's a lot to remember, well, there is, but we can summarize it in this table, and you get this table in your formula book. So don't stress. If you ever need to look these up, it's fine. They're there waiting for you in your formula book. All right, that's all for now. In the next video, we'll put some of this stuff into practice.